Hello everyone, my name is Alex Lemmy, and today I would like to present the paper we submitted to the AABI 2021 Symposium. VIB is half Bayes. The paper is available on the archive if you want to see more. And I have to highlight my colleagues, Warren Morningstar, Ben Poole, Ian Fisher, and Josh Dillon. All right, so what is the story? I hope to basically, it's a very simple story. What we're going to do is I'm going to basically try to tell you that I think there's a middle path. There's a middle way. Instead of having to pull out the entirety of the Bayesian machinery, I think we can kind of go halfway. And in going halfway, we can get some of the benefit without all of the cost. All right, what am I talking about? Let's try and illustrate with a simple toy example throughout. So we're going to start with some data. Imagine we have a data distribution. Let's say we're going to do some regression task. So the x's are going to be uniform from -5 to 5, and the y's are going to be normal condition on the x's. It's going to be a cubic with some uncertainty. Here I'm plotting the 1 sigma contours and the data distribution. From this data distribution, we can draw some data. Here's 10 data points. Here's another 10 data points. Here's 100 data points, what have you. We need to fit a model. In order to fit a model, I need to define a model. Now, perhaps a little different than the way you're used to, I'm going to talk about it in a different way. So we're going to use a neural network, but I'm going to say that, I'm going to have a neural network that's going to, look at the X as the input. It's going to have some parameters. It's going to have a 2-layer, 32 hidden units, say with activations, and then it's going to have a 2-dimensional linear output layer. And I'm going to call that a representation Z. That representation Z is then going to go into some, predictive model. In this case, it's going to be a normal distribution with some particular form using a soft plus on the second component. So, what do we have? We have a neural network that takes the input, spits out a representation, in this case, a 2-dimensional representation, which itself parameterizes a distribution for a predictive model, in this case, a normal. But we're learning both the mean and the standard deviation of the norm. We're learning both the location and the scale. If I randomly initialize this neural network, we sort of get the blue model on the left, again showing the 1 sigma contours. And, we're going to be interested in different ways that we could try to train this model, different sort of risks, different sort of objectives that we could use to try to train it. And then we want some measure of goodness. So as a measure of goodness, we can measure the KL divergence, right? How close the blue model is to the orange data distribution. And so we'll measure the KL divergence from the data distribution to the model, from orange to blue. In this case, the KL divergence from orange to blue is 2 bits. Okay, so how do we train the model? Well, ideally, in a perfect world, what we would do is we would minimize this KL. If our measure of goodness is how close the distributions match, why don't we just make the distributions match? And one way I could express that, again, in a way that, you might not be used to, but I could, look at the predictive model, the likelihood of the predictive model, and I, in an ideal world, I would be able to measure, up to a constant, the KL divergence from the true distribution to our model is just the likelihood of our model where the expectations are taken with respect to the true data distribution. If we could do this is up to a constant, the entropy of the data distribution, the KL, the thing we're interested in. And so if we could do this and we minimize this, then our model should do a really good job. And in fact, in this case, it really does. If I, could approximate this in the computer, the way I do that, right, I don't actually, I can't take the expectations exactly, but I could train with sort of an infinite amount of data in the sense that every mini batch that I ever do for stochastic gradient descent, I draw new data from the data distribution. Then, I train for some amount of time, and the KL becomes quite small. It becomes 12 millibits. So these really do match, right? The blue distribution matches the orange distribution. So yeah, in a perfect world, if I could actually take expectations, if I had access to infinite amounts of data, I can do SGD in order to, maximize the likelihood on, that infinite data, and I do a fantastic job and my model really fits. Unfortunately, we don't usually have access to an infinite amount of data, so we have to do something else. And perhaps, still one of the most popular strategies is to take that original loss that involved expectations with respect to the true distribution. If we only have finite samples in a data set, we can just, make an approximation. Replace those expectations with respect to the true distribution with finite sums, with averages. And that's maximum likelihood training. I just take my finite number of samples, I exchange these true expectations for empirical expectations, averages, and I minimize that. And in this case, if I start with my randomly initialized model and I do the same training, SGD, for the same number of epochs, the same initialization, the same everything, but now targeting this empirical risk, what do I get? I get this. The model horrendously overfits, right? As you might have expected, right? Maybe unlike normal scenarios, you were doing a regression, we're allowing the model to express its uncertainty, but the way it can achieve the best likelihood is, of course, to concentrate as much mass as possible on those 10 data points. And so it does. It goes through those 10 data points perfectly. It goes through them exactly, and it sort of eliminates all of the uncertainty in the model everywhere. And in so doing, the actual Kale divergence, right, how good this thing is at matching the true distribution, really, really suffers. And we go, it's 1,000 bits, basically. Really bad match. We did a fantastic job of doing precisely what we asked the network to do, right? It does a really good job of maximizing the empirical likelihood, but that leads to a very bad predictive model. Fantastic job of what we told it to, but that's not really what we wanted it to do. All right, so what do we do? Well, it's the era of big data. One thing you could do is, this is a bad approximation, but it's only a bad approximation as long as your data is finite. So, you could try to increase the amount of data. And doing so helps. I mean, here we cut the Kale divergence by a factor of 3, just going from 10 data points to 100 data points. So we go to 1,000 data points, hey, now the model matches. It does a great job. Even though our model was pretty expressive, it wasn't so expressive that it can kind of go through every one of these data points, and eventually it just starts learning the true distribution. With 1,000 data points, maximum likelihood, does a great job. So that's kind of the state of the world. That's great, but it isn't perfect. What's another way out? What if we actually only have 10 data points? What can we do? Well, how can we get closer to the thing we actually want, the true risk, the expectations with respect to the true distribution, not the empirical? Well, we all know one strategy, one kind of promise you can make, one path you can take is the Bayesian one. And perhaps this isn't the way everyone thinks about it, but I think it's a good way to think about it, especially in the context of the current discussion. Bayesian inference works precisely because, one way you could tell the story is precisely because it allows you to exchange a loss, a true loss, for an empirical loss, and provides a bound. You can take a thing that you care about if it can be expressed as the expectation with respect to some distribution of a true risk. And you can turn that into the expectation with respect to the same distribution of the empirical risk, provided you add a penalty that looks like the Kale divergence between the distribution that you're optimizing and some prior that you specify, importantly, before you look at the data. And this holds true. This provides a sort of stochastic bound up to a constant term that we can ignore with regards to the optimization, sort of more or less always, to horrendously oversimplify things and not do any justice to the field of pack learning. But this is the thing it allows you to do. It allows you to take things that look like this and turn them into things that look like this, and promise you that that's a bound. And so then when you minimize this, you know that you're still minimizing an upper bound on the thing you actually cared about. And so in the context of what we're doing, if what we really care about is the true risk, this thing up here, we can look at that. And if you notice, it takes exactly the form that allows you to run it through this pack machinery. It looks like the expectation with respect to some distribution of a true risk. This whole thing in yellow, if we identify that as the true risk and we run the pack machinery, what do we generate? We generate an objective that looks like this, where we can exchange the true expectations with respect to empirical expectations if we add a Kale divergence term. And this risk is one that if you minimize it, even though it might not look like it, it is doing exactly sort of Bayesian inference that you know and love. The minimum of this risk with respect to Q of theta is exactly the Bayesian posterior with some temperature tau. And so you can do that, right? Train a Bayesian neural network. If you train a Bayesian neural network in this case, you minimize this risk. Now we need a way to search over the space of all possible distributions over the parameters of the network. Or, you could do that with a sampler. In this case, I used a Hamiltonian Monte Carlo sampler. You do a Hamiltonian Monte Carlo sampler, even though the network has only access to 10 data points, you minimize this risk, and hey, it does a good job. It doesn't overfit. right? This thing is a bound, it's protect us, it's kept us safe, we haven't overfit, and we've achieved a good predictive model. 0.2 bits, really nice. That's great. So Bayes is fantastic, except I think we all know it's also expensive. Is there a middle ground? Is there some way that we could sort of have our cake and eat it too? Maybe we can do only half of Bayes. Hypothetically, imagine for a second, we had our data distribution. It actually has two pieces. It's got the x's and it's got the y's. What if we could go back and we could take that original objective that we couldn't satisfy, and let's only replace one of the expectations with an empirical? What if we could only probe the function at 10 data points in x, but that at each one of those points we had access to many, many target labels? What would happen in that case? Well, we can just run an experiment. This exact same model, trained in exactly the same way, with the exact same initial conditions. What happens? You get this. This looks pretty good. Even though it's only ever evaluated the function at 10 x's, because it now sort of didn't collapse, it had some notion of what uncertainty was at those 10 locations. When you minimize this risk, you actually achieve a model that does almost nearly as well as the Bayesian case. It's 0.3 bits, basically. The neural network does a fantastic job of matching the distribution on those 10 points exactly. In fact, if you measure the KL only on the 10 data points that we asked it to, it does a fantastic job of matching the distribution. But then even, between the points, it interpolates entirely reasonably, right? Just kind of smoothly goes between the points, and for something like a regression problem, that's a reasonable thing to do. And so we end up with a reasonably good predictive model. So now, again, this is impossible. If only we had access to an infinite number of targets, we could do this. But, what if we pull the same tricks the Bayesians do, but we only do it on half the objective? Go back to this true risk, identify that, originally we could have called the whole thing the loss. What if we only call this part the loss? What if we only call the expectation with respect to targets the thing that we want to protect ourselves from? What if that's the only finite sampling that we want some guarantees with respect to? We can turn the crank. We can run the pack machinery. We can, take this orange thing, stick it through here, turn it into this purple thing, and we can generate this objective. This objective, turns out, is equivalent to the variational information bottleneck objective, which has previously been described. But you'll notice it's sort of half Bayesian. We have guaranteed ourselves something having to do with the finite number of samples. We've exchanged a true risk for an empirical risk with respect to the target labels, and then we're just going to close our eyes and hope for the best with respect to the finite number of X samples. And in so doing, we minimize this objective, and what do we get? We actually get something fairly reasonable. The network doesn't collapse all of its uncertainty. It manages to still express a reasonable amount of uncertainty and do a reasonable job of sort of interpolating between the data points with the appreciable amount of uncertainty, and in this case achieves a KL divergence of 0.37 bits. Way better than the MLE. Not quite as good as Bayesian, but this model is much cheaper. Instead of requiring us to have an entire distribution over parameters, this only requires that we have a distribution over activations. It looks very different. It has temperature. That temperature can be important. It can control the amount of uncertainty. It can control these widths, something you might need to do cross-validation for. But I guess to summarize, right, the whole point is just to kind of knock on this door, introduce this new potential path, whereas Bayesian neural networks require that we be able to build or manipulate a distribution over all parameters and protects us against a finite number of joint samples. It's costly and difficult. There's a middle path, a half Bayesian approach that requires only stochastic activations in the final layer, can protect against a finite number of target samples, and remains cheap and easy. And in our previous work, where we only knew this as some information theoretic objective, we've shown in larger scale studies that this can improve generalization and protection from adversaries and robustness in large scale image models, which you should check out. And I think that's the result. Just to finally summarize, maximum likelihood over fits. Bayesian inference is reasonable but is expensive. What if you could try to, instead of be fully Bayesian and target the kind of true risk with respect to both X's and Y's for conditional tasks? What if, for discriminative tasks, what if we instead just protect ourselves against finite labels? You run the same Bayesian machinery, and you end up with this sort of half Bayesian objective. Turns out it's equivalent to the variational information bottleneck objective. And thank you so much for your time.